In this video, I'll be providing an introduction for the doubling time assignment. We're going to be looking at biological processes and mathematics growth curves. At the end of this activity, you will be able to relate time-dependent curves with biologic processes, fit exponential growth curves to data, extract generation times for bacteria from data, and plot multiple data sets on a single set of axes within Excel. The bacterial growth curve represents the number of live cells in a bacterial population over a period of time. In this growth curve, you can see four distinct phases of growth. They are the phase of lag, exponential growth, stationary, and then death. Within the initial phase, the lag phase, it's where bacteria metabolically are active but are not dividing. Therefore, the number of viable cells are not increasing. The exponential phase is where the growth is occurring, exponential growth. We always tell you to label the axes when you're looking at a curve, and this is an example of where it's really important to observe how your axes are labeled. You can see on the horizontal axis, we have time listed in hours, and on the vertical axis, we have the log of the number of viable cells per milliliter. Our claim is that the second phase is exponential, although to the general eye, you would claim that this looks like it's linear growth. But because our scale of the vertical axis is in log of number of cells, this linear pattern is in fact exponential, and if you were to graph this same phase for just the number of cells and not the log number of cells, you would see the exponential curve. Phase 3 is a stationary phase where the growth reaches a plateau as the number of dying cells equal the number of dividing cells. The last phase, which appears to have a constant decrease, represents the death phase and is characterized by an exponential decrease in the number of living cells. Again, remembering that our vertical axis is in the log number of cells, therefore this straight line on our curve is in fact exponential decrease. In an experiment, you can observe and actually measure the number of bacteria present and plot your raw data in Excel. Mathematical equations, such that we looked at in the exponential and logarithmic equation units of this course, are used to describe what happens in real-world experiments. We often claimed within our examples that a particular bacteria experience exponential growth. And in practice, we can see that that doesn't occur over the entire life phase of the bacteria, that it's only a small portion of its growth that is exponential. Different organisms can grow according to qualitatively different types of graphs. You can see 4 different growth curves shown here, and you can suggest an organism that could follow these particular growth curves. You can actually also make a different graph to describe an organism that grows in a particular fashion. If you know which phase the growth is in, therefore the shape of the curve that you're expecting, whether it's constant or exponentially increasing or decreasing, as well as the number of cells or bacteria existing at particular moments in time, we can determine an equation to describe that growth. In the course to date, we've looked at exponential equations of the form y is equal to a times b to the power of x, where a and b are both constant. A represents the initial population, and b represents the base of your exponential equation. We can rewrite the same equation in the form y is equal to a times 2 to the power of r to the power of x. As you can see, we've taken 2 to the power of r and replaced b with 2 to the power of r in our initial equation. A is still your initial value, so the value of y when t is equal to 0, and we call 1 over r, it is our doubling time. When we refer to the doubling time, we mean the amount of time that it takes for our population to go from our initial value of A to being equal to 2A, so doubling. So again, it's important to note that the change of form is from taking B and setting it equal to 2 to the power of r. And we can solve for r using our exponential and log forms. Here we're asked to determine the doubling time for a certain bacteria. So it says, what is the doubling time for a bacteria population that increases from 10,000 cells to 10 million cells in 4 hours of growth? The first thing we're going to do is take the data given in the question and put it into a table of values. We have two pieces of information. We know about our variable of time, which is given in hours, and then the number of bacteria. Initially, at time 0, so at 0 hours, we have 10,000 cells present, and then after 4 hours, we have 10 million cells present. The first step is to fit the data to our exponential equation. And I'm referring to our general exponential equation, so y is equal to ab to the power of x. We know a is equal to our initial value and is therefore equal to 10,000. This means the equation that we're looking to build is of the form y is equal to 10,000 b to the power of x. Now we need to determine the base of our exponential equation, so we want to find the value of b. To do so, we use the other point in our problem, so the point where after 4 hours we have 10 million cells present. I'm going to actually change the variables in our problem to relate to what I put in the initial table of values. Okay, so now if we sub in what we know that we have 10 million cells at time t equal to 4. Now this problem reduces to an equation in terms of one variable. So we only have b as our missing variable, which we can solve for. The first step to solve for b is to divide both sides of the equation by 10,000. We know 10 million divided by 10,000 is 1,000. So this equation reduces to 1,000 is equal to b to the power of 4. To solve this equation, we want to determine what the value of b is. Therefore, we need to consider what is the opposite operation of a power of 4. So since we have b to the power of 4 and we want to find b, we need to take the fourth root of both sides of the equation. The fourth root undoes that power of 4, and you end up with b being equal to the fourth root of 1,000. So here this reduces to 5.6234, and our equation describing the growth of the bacteria can be expressed as y is equal to, I'm going to go back to our n variable, n is equal to 10,000 times 5.6234 to the power of t. So you might be wondering whether or not the equation that we've used to describe this population growth seems reasonable given the information that we know about the growth. We know that at time 0 we had 10,000 cells, and that's represented by this point here, 0, 10,000. And then we know after 4 hours we have 10 million cells, and that's represented by this blue dot here. I've plotted each of these points using some graphing software, desmos.com, which is freely available to you. So it's a great tool, as well as GeoGebra. You could also confirm in Excel. And what I'm going to do is graph the equation that we use to describe this population growth and observe what happens. So now I'm graphing 10,000 times 5.6324 to the power of x, and you can observe that our exponential equation does in fact go through each of the given points. So it goes through at 0 and as well as after 4 hours. So we can use this equation to predict the number of cells after a certain period of time. So the next step in determining the doubling time is to rewrite our equation in the form n is equal to 10,000 times 2 to the r x. To do this change, we're substituting b is equal to 2 to the power of r in our initial equation. We know that b is equal to 5.6234, and it's equal to 2 to the power of r. And now we have an equation in terms of a single unknown, and we can use r to determine our doubling time by calculating 1 divided by r. So first things first, let's solve for r. We have an exponential equation, and we're looking to solve for the exponent. So we should solve the exponent by rewriting this expression in log form. In log form, we get that r is equal to log of base 2 of 5.6234. Now we can evaluate the value of r by calculating log of 5.6234 divided by log of our base of 2. And each of those logs are log of base 10 on your calculator. So we calculate the value of r as being 2.4914, and we can write the equation for the number of cells as being equal to n is equal to 10,000 times 2 to the power of 2.4914 t. And now you want to think critically if this seems reasonable and equal to the original expression that we had for n, because we're not wanting to change the appearance or the value of the original equation. We're just looking to re-express it with a new base. So we wanted to change our base from being our b value of 5.6234 to having a base of 2. Now we're going to plot that equation in Desmos and confirm that it is the same as our original equation. Now plotting our equation with a base of 2, y is equal to 10,000 times 2 to the power of 2.494. Our exponent is 2.4914 times x. And you can see that it is in fact the same function, just re-expressed using a different base. Another way to confirm that our change of base is actually correct is to evaluate 2 to the power of 2.4914 in your calculator, and you'll get your original base of 5.6234. Now we're ready to calculate the doubling time. So our third step, calculating doubling time. So we know that the doubling time is equal to 1 over r, which can be written as 1 divided by 2.4914. This is equal to approximately 0.401, and we would record that final value in hours, and that tells me the amount of time required for our number of cells to go from 10,000 to double of that, so 20,000. Now you've arrived at a final value. It's always good to double check. You can either go to Desmos or perform a short calculation by hand to determine that this is correct. You can check using either equation. So we can check using y is equal to 10,000 times 2 to the power of 2.4914 x, or t. And when we sub in our value of t, we end up finding that the number of cells has in fact doubled and is approximately 20,000 at that time. So now we've calculated the doubling time. Best of luck with your assignment. Let us know if you have